For example, his background is quite interesting. He started his studies in Australia, did his PhD with Professor Wiseman, who gave a talk right here.
This meeting is being recorded.
And then moved to postdoc position in Yale. Yale is the sort of mecca of quantum computing, superconducting quantum computing. Anybody who is anybody in quantum computing, particularly experimental area, superconducting qubits, has something to do with Yale. And then he of course went to Waterloo. Waterloo is another mecca. So you can see then in 1911 he moved on to industry, and you see what we are using in IBM is essentially his creation, because if you see, he's a vice president now. He has a foot in technology, another foot in science, and that is what he really required, because just technology doesn't work, just science doesn't work. So he became an IBM fellow in 2016, and American Physical Society 2014, fairly young age. And then, he is also the vice chair of the APS Quantum Information Division in 2017, which is very, very creditable. Now, if you see his public citations, publication, H-index is quite remarkable. So, great thing is that you are still doing good science. That's what I was looking at your publications. So we are really looking forward to your talk and see what kind of science we can do in IBM. We have been using it quite extensively. This Rahul, was our student here, was working with you, and many other students have been using IBM. So thank you so much. And I'm specifically grateful to IBM to have, given this opportunity where you people are really training our students, of course, in an all India basis. And some students are also from Bangladesh, Nepal, Sri Lanka, it's a pan-India kind of thing, nearby countries. So welcome again. So please go ahead and give it up.
All right, thanks. Do you want me to start?
Yeah.
All right, just let me 2 secs. PowerPoint share. Sorry, is that showing properly?
Yeah.
Okay. So, 2 secs. So I'm going to give you a bit of a talk. If you got any questions, please ask them. I'll give you my view of where we're going and how I see applications being important, and a little bit of a review of quantum mechanics. It's my pleasure to be here and give this talk. So in 2016, as was mentioned, we had this idea of putting the quantum computer on the cloud. What I'm most happy about is actually how many papers I've seen get used using the machine. Seen over 500.
The recording has stopped.
Seen over 500 papers using our machine. To me, is a great example of how science can be done by bringing this tool to users and many other scientists like you guys that are using it. And the other number that I really like to see is how many circuits per day. We're up to 2 billion circuits, and that really shows the demand of these systems. So as was mentioned, I've done superconducting qubits, but the way I look at this now is, sorry. I see the question, is building systems. And so I've transitioned myself from thinking this more as how do you design systems. So to me, we took a lot of pleasure in calling out the IBM Quantum System 1, and that's because this is everything. It's the control electronics, it's the cooling, it's the attenuators, it's the amplifiers, and it's also the quantum processor. But it's this system view of building it. And the system view is what has allowed us to put so many systems online. Today, we have over 20 systems online, and this is just a screenshot showing some of them. Each one of our systems is, we name them after a bird, and the bird basically identifies a processor family. Falcon is a 27-qubit processor, for instance, and there's Falcon R4 and R5 are our latest revisions of this, with R4 being our standard and R5 our new technology of integrating faster readout into it. And then Hummingbird is our 65-qubit. And as you'll see in my talk, we're working on larger and larger systems that we've named after different birds. But you can just think of a bird as identifying a new processor. Here's Here's a cross-section of what we like to show for one of our devices. This is the Calcutta device. It's one of my favorite devices because it's an R5. And in this R5, we've actually integrated fast readout. And you can really see these improvements in the numbers with the 2-qubit gate being pretty good and the readout assignment error going into the 10 to the -3. And we have this philosophy that much like the users, we want to do our science on our premium devices, and that's why we want to get them up as fast as possible. And this philosophy really drives us to put the best devices online and then to do our fundamental science with them. And some examples of that are these papers that are recent papers from our group, which is the first 2 focus on quantum volume, and the last 3 look at different types of applications that we've done looking at quantum computing. And last bit before I go into a bit more details, I was very excited to see. The APS is a huge talk and a huge conference in America, and the fact that there were 46 papers using our devices really says to me that we've built a tool that is good for science. And some of the science that we've seen others do is like these paper by the Australian team. What they looked at is different ways of characterizing the devices and claim to measure the most entangled state on a system and demonstrating entanglement on 65 qubits on the Manhattan. So let's just take a change of gears, and I apologize, I keep coughing. I haven't been feeling the best lately. I look at quantum computing as the first time computing itself is branched. Computing, as you know, has had a large history and has impacted everywhere in our lives. We have computers in our pocket and things like this. But every one of these innovations in computing was essentially just a new version of doing something different in the same model. And so what has happened with quantum computing is it's the first time it's actually branched. And now there's 2 different models of computation. And going forward, we'll look back and call this classical and quantum. And I think this is a big deal because when we get these new type of computing and this new type of math, you got to ask yourself, well, as we can scale this math and do great things with it, what type of applications can be done? And I'm really looking forward to seeing that. To sort of give you a feel for the way, and I know you've done a few introductory courses in this summer school, so I won't go too much into this, is that I think of quantum computing really in terms of the quantum circuits. And the quantum circuits are these instructions for running a quantum computer. So they start with basically, what you do is you start with some problem. Hopefully it is an important problem. Solve some chemistry, find the ground state. There hopefully exists a polynomial efficient algorithm that's classical that turns it into a bunch of circuits that run on our quantum computer. And these circuits start with initializing the qubit and doing some gates, either 2-qubit gates, single qubit gates, some measurements. And so this circuit will take the qubits through some type of evolution, measure it and turn it into classical data. And we hope that this algorithm will be polynomial in the size of the problem. And then ultimately it'll come and feed it into a solution to this type of problem. And so this general structure is what's called the quantum circuit model. And what we can show is all the classes of quantum computing emit efficient quantum algorithms in this model. This model, though, is still really a pen and paper model. And I like to go a little bit further and say, well, in quantum circuits, we need to generalize them a little bit more than the standard model, and we need to bring into them other types of features. One of the most important is to bring some classical compute. And a classical compute where I make some measurements on my circuits, and depending on those measurements, I do things in the future. The most famous of that is teleportation, which shows that I can take some quantum state on qubit 0 and map it to quantum state qubit 2 by using an intermediate state and classical measurements to correct for any error, correct for the measurement collapse that happens as we do this process. Another example, which I like to highlight, is any Clifford operator. And if you don't know what Clifford operators are, just consider this one here. Imagine I have the problem if I wanted to do a Hadamard, and I wanted to, I wanted to take qubit 2 and generate an entangled state over all of the qubits. One way to do it is you start with a Hadamard, which creates a superposition, and then you C-knot it, which entangles qubit 2 and qubit 3. And then you start to walk out the tree by entangling more and more qubits in. And the GHZ is going to take a time to create this resource. It's going to take a time that is proportional, we call it the depth, to the number of, basically the number of qubits that you want to entangle. Okay, so you see that, and many, here it looks like, well, if I only have nearest neighbors, it limits how well I can get this entanglement out. Well, what can be shown is you can actually do this with measurement and feed forward in constant depth. And here's a different type of circuit where I measure the parity, so the joint ZZ between the two types of qubits, and then I feed forward this result, and I meet the parity between qubit 2 and 3 and feed forward this. And then by doing a simple correction and post-processing here, I can create the entangled state. And so what this can sort of show is that any Clifford operator can be reduced to constant depth with feed forward, and that includes swap and things like this. So by adding classical real-time compute to a quantum circuit, you can get rid of limitations that connectivity imposes on your system. And as a simple example, we took the Bernstein-Vazirati algorithm, and it's a really algorithm that basically C-knots all the different qubits to an auxiliary qubit, and then you measure the fidelity of this auxiliary qubit to determine how the algorithm performed. And as a function of the bit string weight, you can see that if you actually are restricted to just types of swaps, you get a big suppression of the result. However, if you've got arbitrary connectivity like they have in iron systems, you get a much better fidelity. But by bringing feed forward in, you can reproduce the same fidelity as connectivity and reproduce the result and allow you to go to a bigger problem instance. So this sort of highlights how you can use feed forward as an advantage. You can go even much further. So for those, I'm sure many of you have heard about this thing called the quantum phase estimation algorithm. Essentially what this algorithm is a way that you can determine some phase of a unitary operator. And so imagine this is important for many applications, i.e. chemistry. You may want to determine the eigenvalue of some problem. There are many ways which you can do this. The most famous is the quantum Fourier transform. But here I highlight two other alternatives. The first one is due to Kataev, and what this one does is you take your phase and you represent it out in a bit string of each variable, and then for every bit of accuracy, you do an experiment of applying, we call it a Hadamard test for measuring the cosine, and a Hadamard test for measuring the sine. And then by the combination of the cosine, measuring that, the combination of the sine, measuring that, post-processing it, you can determine the theta for bit k. Another way you can do it is you can do what's called iterative. Here, it's very similar to the sine test, but what I do is my previous estimate of the bit, I apply a phase correction to correct for that, to leave just the next phase. And so by doing that, I can just measure one, I can just measure it, feed forward, measure the next bit, feed forward, and measure the next bit. And so what this sort of shows is you get this, as we're advancing these types of circuits, you get this trade space between doing classical processing of circuits and real-time feed forward of circuits. And whilst, and you can investigate how this observes. In this paper, we showed that for limited resources here, say 30, the Kataev method gave less accuracy than this method, but as the resources quickly got around in the couple of hundred, they became the same because coherence started to affecting both of them. But what this highlights is in the near term and going forward, you're going to have this trade space of mixing classical and quantum to look at different types of problems. And so this gets to what I like to call the definition of the extended quantum circuit. And this is a quantum circuit is a computational routine consisting of coherent quantum operations on quantum data, such as qubit, and concurrent real-time classical computation. It is an ordered sequence of gates, measurements, and resets, which may be conditioned on the use of the data with real-time classical computation. So this definition of the extended quantum circuit, it drives the hardware that we want to build and drives how we want to develop applications that use it. So to do that, before I go into sort of giving you a review of the hardware roadmap, there are three fundamental things that matter for basically for determining how you're making progress on this extended quantum circuit. One of them is quality. How good is the quantum circuits that you run on your system? We've chosen this metric of quantum volume to measure it. I don't really mind which metric you use, but think of this as just measuring how good is the machine obeying quantum mechanics. The second, as I said, you can trade classical and quantum resources. So if you're doing that, you need to run these extended quantum circuits at a really fast rate. And so the quantum processing speed becomes another very important metric to monitor. And then the third is, with these extended quantum circuits, you want enough flexibility to do many types of interactions, many types of circuits. And so we need to have a rich set of operations that can be done. And so I call this variety. So we've laid out a roadmap for increasing the qubits. As I said at the start, we have the 27 qubit system online today. We have the 65 qubit online. We're working towards the 127 qubit this year. Next year, we'll put out the 433, and then in 2023, the 1,121 qubit system. So what went in to enable the Falcon and the Hummingbird? Just to go back in history and to give you a bit of intuition of what are the key enablers that made it possible. The first is the Falcon is an architecture which we call the heavy hex. So it has this architecture where every qubit only has two neighbors, then three neighbors, two neighbors, three neighbors. So this gives us an ability of stacking qubits with high frequencies, low frequencies, high frequencies, low, low, high, low, and so on. And so what you can imagine then is you can try and set the qubit frequency so that you don't have collisions. One of the things that limited the systems before were too many collisions made these devices not operational. So here is a plot that sort of shows a histogram of the fluctuation in the qubit frequency. And if you have the standard way of making qubits just to fab variations, you find that you get basically 300 megahertz of frequency spread, and this leads to many type of collisions. So what the team did is they came up with a technique where we would use a laser and we could post-tune the qubit frequency after fabrication, and we could drive one to a high, low frequency and such, and this is what's shown in the black. Doing this allowed us to get a much higher yield for these Falcon chips. Now, going to higher qubits, you actually have a problem. So if I had all of these and I imagine that I had to have a readout for every type of qubit, I'm going to be limited by how much amplifiers I have in my system. And so to enable the 65 qubit, we worked on this technology of multiplexing many of the qubits together to read out. And this multiplexing technology gives us the ability to have one amplifier for eight different qubits. And this reduces the amount of overhead that goes inside the fridge to reading out the devices. And the multiplexing really enabled us to go forward. So those two things key were what enabled us. And as I said, the quality is also a very important metric for us to measure how we're making progress. And the quantum volume is a heuristic way of doing this. And essentially what it is I just randomly choose to do a 2-qubit gate between a random pair, pick another random pair, another random pair, and then I calculate the amount of layers, which we call depth, that I can run a quantum circuit where the width and the depth is such that I pass the threshold. And that threshold is just chosen to be an arbitrary number. It's 2/3. And if I can cross that threshold, I say that I can achieve that type of quantum volume circuit. And our goal is to keep showing that we can achieve longer and longer and wider circuits. And so this becomes the metric for the quantum volume. The reason why it's very good is it's very heuristic number. If I was just focusing on 2-qubit error rates, I can imagine that I would optimize just the 2-qubit error and not see the global effects. So for example, to achieve a quantum volume of 64, we had to do a combination of 4 different things. The first was actually improving the software, coming up with more efficient ways of doing compiling. And this really shows a path for a lot of innovation using these tools as we develop the compilers of the future. How do I take some type of operation and turn it into the most efficient set of gates that can run on my system? So optimizing the compiler was a huge step. Another step was designing a new gate that could be shorter in time and run with slightly higher fidelity. So previously we did the C0 that was double in time and had an echoing sequence in the middle. And now we switched to what we call a direct C0, which allows us to do all of the gate in about 30% saving in the 2-qubit gate time. Now, on top of this, because we got rid of the echoes in our 2-qubit gate, we needed to introduce echoing sequences that refocused errors when we were not doing gates. So here is an example of inserting a pi pulse that will cancel some slow noise, and then we'll have a correction pulse later in the time, but we spread them through our circuit, and this is called dynamical decoupling. And the fourth is, well, if you have access to the actual system, pulse level and the pulse level controls, you can do things like boost your readout by using the higher states of the qubits, and this was the fourth part. Putting all that together has allowed us to achieve a quantum volume of 64. Then to go further and get to 128, it was a combination of just continuing to push the compiler to get even more compiler improvements by using the fact that certain C0s work better than others, so making the compiler hardware aware, and by taking the readout and putting machine learning type algorithms in there to give linear discriminators and quadratic discriminators to give slightly better boost in the readout performance, allowed us to get a contour which determined whether the qubit was ground down or up, that gave a slightly improved readout. And this allowed us to push to 128. So our progress has basically been that we're committed to doubling our quantum volume each year. And our goal is to keep pushing this so we have higher and higher quantum circuits that will run on our system. And you can see where for 2021, we overachieved. But going to our next goal is to get to this year to 256 and things like that. And these get more and more difficult as the system gets longer. So I expect this will keep following this line for a few more years. So now that we can reliably make 65-qubit machines, how do we see the path towards making bigger and bigger machines? So if you imagine you have this type of device, and you needed to have control lines that could come in and drive all the qubits, you have basically an I/O problem. And you have an I/O problem because all the control lines, if I go to this one, this one, this one, this one, and so on, they can't cross, right? They'll go in and then they'll come down through the plane and bump on into the qubit. But I have basically a restriction on how many lines I can have in the top. To solve this, we borrowed techniques from classical computing of making the flip chip, the interposer, multi-level wiring. So here you see the wire would come in, come down. You could imagine another one coming along, coming down, coming back up, and going along. And so this required building multi-level wiring as well as through silicon via technology. Doing this gives you the ability to control systems of this size and really solves the packaging and wiring problem. And so we're well on our path to demonstrating this, and this is why we have very high confidence that the Eagle will be out this year, and our future devices will come out as well. To go beyond this, So if we've got technology that focuses on the packaging, we start to get limited by cryo problems like cryo infrastructure, the amount of density of the lines, and how many input outputs we can have. And so the team has been working on what we call cryoflex cables. And so these are bendable cables that have a waveguide in that essentially replace all these cables that you've probably seen in many types of pitches. And this allows us to have a much higher density of lines that go into our machine. And for this, we believe we'll go forward and solve the cryo density problem. Here's just a more zoom in showing the multi-level wiring and of a cross section, and you can see that you can jump between the different layers and that effectively allows you to jump over the lines. Getting towards 1,000 and pushing the error rates down to the rates that we want to get, it actually comes back to the fundamental gates. And basically, the fundamental gates will continue and always be the problem. But we've had 2 recent papers that we've put out where we've shown different ways of doing the gates that can get about a 5 times improvement over our system in gate performance. The first is using a tunable bus, so we can do a ZZ type interaction between 2 qubits. And the second is to use a interference bus, so we can do the same cross-resonant gate we've done before, but have less crosstalk and less of unwanted interactions. And doing this allowed us to drive the gate faster and have a faster, higher fidelity. So both of these are different types of gates that we're integrating into our multi-qubit devices, but this is what will be needed as we keep pushing higher and higher qubits with better and better fidelities. So my view on the quantum processes, we must investigate all these problems in parallel. The biggest problem always is coherence. Material science will continue to be limited in the quality. The junction physics, we have to keep working on it. As you saw, the heavy hex and the laser annealing solved a lot of the yield problems. But as you get to larger and larger devices, this yield will always still come up as a problem that we need to keep looking at. And getting beyond 1,000, we have to introduce concepts of modularity, some type of quantum interconnect. Some early work we're working on is trying to couple qubits to optics. Here we show a silicon germanium cavity. We've achieved a high Q of about 150 million. And our goal here is if we can have a high optical cavity in silicon germanium and we can build a qubit next to it, then we can couple the qubit to the optics and then hopefully couple the optics to another qubit in a different type of fridge and chain multiple different fridges together in a distributed network. There's a lot of science that needs to be done to make this possible, but this is just a demonstration that we've got some early science exploring the path towards this type of distributed approach. All right. So I wanted to take a change of direction and give you my views on how applications will work on these type of systems and how we should be exploring type of applications. So we have 2 circuits here. The top circuit is actually easy to calculate. The bottom circuit, we believe to be difficult to calculate as it scales up. In the top, it's basically comprised of Clifford operators, and all I've done is replace these type of Clifford operators with arbitrary single qubit operators, and that makes this sort of complicated. So you can ask the question, what makes a circuit hard to simulate? Sadly, the answer is not simple, and there's no simple known criteria. But what we know is we need a lot of entanglement, else the tensor network contractions are going to be able to do it. We need the ability to interfere. So we need the ability to do quantum phase gates and things like that. So we can have coherences interfere and have negative interfering. Otherwise, quantum Monte Carlo methods will work. And we have to have complicated algebra. If our algebra is just the Clifford circuits, as I said, that's easy to do. So we need some complicated algebra that's built into it. So on this, what I always view and what we look at is the complexity theoretical hardness of the quantum circuit is the only reason a quantum application will have a quantum advantage in computation. There's been a lot of work on this, obviously starting back with Barbara Terrell and David DiVincenzo on trying to actually look at post-selection on constant depth circuits and what is hard by that, with a few following papers on IQP circuits, as well as correlation and obviously the super polynomial simulation type algorithms of Scott Aronson. So our team, from my team, Sergey Bravi, working with his colleagues, David Gossett and Robert Kong, did show that for a constant depth, they could prove a separation between classical and quantum. So this gives us hope that there is this difference between classical and quantum. And this was a simple GHD type game experiment. I don't want to go into the details of this other than to say they give us a grounding and a framework for us believing that there'll be a separation between circuits, even with shallow depth. So here I try and take a transition into a type of application. Imagine you had a machine learning problem. You had basically two colors, light blue and dark blue. And I wanted to be able to separate the light blue from the dark blue. One way I can do this separation is I can enlarge the dimension of the space here, quadratic, and then I can put a separating line between it. And then once I can do that, I can say the light blue is different to the dark blue and easily separate it. So inspired by this dimensional mapping, which is essentially taking some data and mapping it to a function space, we looked at this idea of, does this apply in machine learning? So now you have a quantum circuit, you have some data, input X, you apply it to make a map, and so the map is essentially a data X to some operator that's represented. Now, the rest of it is standard classical. If I have some way that I can efficiently measure this kernel, and one way I can measure it obviously is a swap test where I can have an ancilla qubit come in and I can have the two different circuits controlled, swapped, and I can measure the overlap, or I can apply the circuit forward and then apply the following circuit and measure the probability of projecting into the zero. If I can sample this kernel efficiently on a quantum computer, and there is some type of mapping that only a quantum computer can do, I can feed the rest into a classical problem and then apply standard machine learning techniques to investigate it. So what we noticed is that a lot of the QN quantum neural network heuristics are compressed to this because quantum is only linear. Global phase is not detectable, so you have to use operators. And finally, we need hard feature maps. Product states won't work because product states, I can then calculate this efficiently. Coherent state displacement, so sort of Gaussian states become efficient as well. And even IQP circuits, which are a candidate for hard circuits, it's still easy to sample with them up to additive noise, so they are not a candidate. And to go a bit more details, you can imagine you could have, here's an example of a product state. This one's trivial, whereas here's an example of something that is not a product state where I have basically an entangled operator where I have the data encoded in the Z's, and then I apply the encoding in this type of circuits. This actually is what's known as an example of a correlation circuit. And so based on the fact that this type of circuit we believe to be difficult as we scale it up, we then ask the question, can we use this as a primitive to look at machine learning? And so we were using the computational complexity of the circuit, showing that we could put the data, encode the data, we could map it into a kernel problem, and then we could investigate it on an experiment. And so when we did this, we found it worked with high fidelity reasonably well. And so this definitely suggested a path going forward for machine learning using these kernels and using the primitive of complicated circuits. Oh, sorry. Since then, we've formalized it for data given different types of group structure. So now you imagine I have some type of group that is parameterized by some operator D that takes in the data. And now I want to apply that to calculate some type of unitary. And I want to apply the D dagger, as I said, to reverse it. And the difficulty here comes on finding the right fiducial state for this chosen group. And so now I could imagine having my group data, I could map it up into this larger space by some D operator. And then I'm left with the problem to determine which is the right fiducial state. And so this casts itself as an interesting problem, as we can say, well, if I can find the fiducial state, then I know which fiducial state to put in. I can then apply the D, and then I can do a hard problem. This is exactly what the team did, where they encoded the problem of modular multiplication of integers, which is very similar to Shor's algorithm, into a machine learning. They found the operation that represented it, plus the right fiducial state that went into it, and this allowed them to basically prove that quantum kernels can exist with a super polynomial quantum advantage. And so now you can ask the question, well, if I don't know this in general, can I actually come up with a framework of using a classical computer to train it to find the right fiducial state? And so what we did is we developed a method that we call quantum kernel alignment, inspired by classical from classical computing. And so this then is trained. We then minimize this V by minimizing another simple classical optimization problem. And for experimental demonstration, we took the problem of generating a group that is a rotation, arbitrary rotations of Pauli's, which is given here by RZ and RX. And then we know that the graph state would be the ideal state. And so we parameterized the graph state and allowed the quantum computer, the classical combined quantum computer, to see if it could find the right problem. And experimentally, it worked. We found that lambda started off with pretty bad cost. We minimized the cost and found the right. And once it went down, the test accuracy went up, and it started to find the lambda, which would create, in this case, a state that got closer and closer to the ideal graph state, which we could theoretically prove is the optimal for this type of group and chosen operator. So this suggested that this method works. How we generalize it is still an open question, but it gives us another ability of now realizing that we could use groups to encode the problem, and we can now use kernel alignment to find the correct fiducial state. The open question still remains is, what group do I choose for different type of data? And that will always be a really hard question, and I hope to see different ideas keep pushing and trying to determine this. Okay. I don't want to go into many details of this, other than give you a sort of a view of how I see quantum changing in the future. So another type of problem which is very popular is this measuring a type of Hamiltonian. And so it turns out that chemistry, if I can find the ground states of a molecule, this is an important problem for determining various different properties of chemistry, like reaction rates and so on. Sorry. Essentially, there exist efficient algorithms that can map a chemistry Hamiltonian to some set of Pauli operators. Once I can do that, I can then extract the energy by simply sampling those Pauli operators, and then I can calculate on a classical computer and update it. So what we did in this paper, and all I want to sort of point out, is we chose, again, a circuit family that we believe comes from the quantity that is easier to implement, but we can prove is going to be of a form that we believe to be difficult. And essentially it's a bunch of single qubit operations, a diagonal operation, a bunch of single, and we repeat this multiple times. And so what we wanted to show in this is we could come up with hardware efficient ansats and still be able to solve a chemistry problem. And because these were hardware efficient ansats and they were easier to implement, it allowed us to explore larger molecules for the first time pretty fast. And it showed that they found the right value. And for H2, it worked pretty well. For lithium hydrogen, it started to fail. And for lithium hydrogen, it had more noise. If we zoom in on this one, the second one, an interesting thing happened. We followed it up with ideas of, well, if I only care about an observable, are there techniques I can run more and more experiments where I can process those results together to give a better estimate of an observable? And we called this error mitigation. And it turns out I can error mitigate on circuits, I can error mitigate onto measurements, but it turns out that for this lithium hydrogen, I could make a 10 times improvement actually in this contour. And the features that started to show variations disappeared. And this is because we allowed the ansats to run longer. And so now we had more of the circuit could explore more of the quantum space to find a better solution. And so this suggests that we need these type of techniques that I can add classical processing on top of quantum. So all of this comes together and sort of gives you this idea, this framework that in the future, we are going to be mixing classical and quantum more and more. And there's various interesting ways. Like there's this idea that dates back to Sergei Bravy and team, that if I wanted to simulate a quantum resource, I can simulate it with classical, where I can basically put more and more classical bits in to do larger and larger quantum. And they did a theoretical framework back in 2016. There have been generalizations of this, generalizations where the team, where people have taken a quantum circuit, and by cutting across this quantum circuit, inserting a qubit where you measure and prepare all the different types of states, you can then simulate larger and larger circuits. And there have also been other techniques where if I cut across a certain symmetry, I then can sum across that symmetry, and then I can calculate a larger type of circuit. So all these are suggesting that by taking a quantum circuit and cutting it in different ways and bringing classical compute in, I can look at larger and larger problems. This is exactly what the team did for a water demonstration. So they used the fact that the symmetry in the water to come up with an ansatz. This ansatz could be cut in simple ways. Obviously, here it's cut over a certain wave function. And then by summing up the results multiple different times, you could measure 5 quintillion different observables. And by putting them all together, we could measure many, many, many circuits and combine them together to give a large type of problem. And so this is suggesting that to run some type of experiment, you're running 10 I don't even know how to say the number, but 10 Q number of expectation values, which is a ridiculously big number to look at certain type of applications. And by using this technique, they were able to map out water. And by mapping out water, they could look at the different types of symmetries, different types of molecules, bending angles, and study the contours and the energy electrons as a different type of function of the parameters of the water. So I'm going to skip this. So what this leads to is it leads to us needing a lot of software. I'm not going to go into much details in the software other than to say we've developed Qiskit. I'm sure many of you have used it. It consists of compilers, visualizations, tools for benchmarking, and it has a bunch of application modules that give a way to framework the applications. But what I'm excited by is where we're going in the future is this thing called the Qiskit Runtime. And the Qiskit Runtime is a new programming model that is going to give you the ability to do classical and quantum together. And basically what we're introducing is this thing we're calling a quantum program. And the quantum program now is going to exist in a way that it can exist on classical servers we could imagine they could be where the users are, or just on cloud services in the cloud, or on IBM classical services that we're putting very close to the quantum computer, to the qubit. And so by giving this type of program and a technology that allows us to move the quantum program between different types of classical computes, we can have part of the program focus on really accelerating circuit execution. If I've got to run 5 billion or as I said, for the water, 10 quintillion, that's a lot of circuits. And if I'm running 5 billion circuits and I take a few seconds to run a circuit, you can estimate that it's going to be a ridiculous long time to do any type of research on a quantum processor. So if we can get this at the millisecond time, which is limited, which is one of the reasons why I really like superconducting qubits, we can be limited by the QPU time of our device, and we can run these in a reasonable amount of time, like a day or something like that. And so this then gets us a new type of API that we're working towards, where the user will call and be able to call remotely a quantum program, load up a program. The program will have the ability to work on different types of architectures, and it will return the results. To do this, we've had to do two different types of things. I'll focus here on the left first. We had to focus on redefining what a quantum circuit is. As I said at the start, I want to give you the ability to do real-time calculations. So we had to develop a new assembly language. We're calling this OpenQASM 3. And in that, it gives you the ability to write operations that call out to real-time architectures, which can do classical computations like measure and do something, and it gives you a framework of doing that. And then on the left, we need a containerized technology where we can build a runtime job that can exist basically on various different classical compute, and we can allow the computation, if it needs to call a lot of classical compute to do, say, the breaking of the problem, the cutting of the problem, the analyzation of the problem, it can leverage with that classical compute where it is. Or when it's streaming the results to get the most out of the system, it goes right next to the system, and then it can actually extract the data at a really fast rate. And so I see both of these as essential for what we need to do to make quantum computing go the next step in the cloud. And as a final example, this lithium hydrogen that I discussed really briefly, it has about 5 billion circuits, and with about 25 circuits per section value. If I was to compare it with the previous methods that we have, where you did most of the jobs on your computer and send it, you get pretty distributed and slow operation. With the new runtime that we've just released in beta, you see that this time is at least 5 times faster, and the distribution of the results is even smaller. And as we go further forward in time, we'll continue making further improvements that push this down to basically being limited by the QPU time of our system. So to conclude, we've laid out a map of how we see quantum computing. I told you about the different type of hardware and our path towards 1,000 qubits. I've told you that I see circuits as the fundamental, and we've got to keep developing those circuits. We're working on different ways that those circuits can be used in different types of applications. And to enable those circuits to run at really fast rates, we've released the Qiskit Runtime. It can give you a very fast improvement. Just the runtime itself gives you a 5 times improvement, as I showed on the last page. And we're well on the path to these dynamic circuits, so you can investigate, feed forward, and do the full extended quantum circuit by doing the combination of dynamic circuits with the hardware. And I see in the future, as we build towards 2023, we'll take these Qiskit runtime containers and we'll keep working up the cloud to build more and more application workflows and bringing quantum to where the data is. And on that, I'll take some questions, and I hope you enjoyed my talk.
Thank you, Jay. Thank you very much for being here and telling us all about new quantum computers, which IBM will be giving us soon, and the technologies and the improvement, what we can expect in the upcoming era of quantum technology, and also the improvements right now. There's so much in this talk that I've learned, and I expect that more will be coming. So we have some questions.
Yep.
Okay, so first one is application of QC to reduce runtime. For that, graph search algorithm take too much time in normal machine learning. So do you think is it possible to find a quantum computing algorithm, or is there a way already known which can improvise it using a quantum computer rather than doing it classically?
Yeah, without going into details on that, I think the most likelihood is only going to be a polynomial improvement. It feels like it's an algorithm that is more going to only be able to exploit things like Grover's. I'd need to know a little bit more details of the actual algorithm, but my initial guess would be best case polynomial.
Another question. So how much time do you think it will take for ideal quantum computation to be possible?
So I think what is meant here is error correction. I believe in error correction, but I don't believe that it is you have no error correction and then error correction. In fact, I skipped over this because of time, but one of the work that I was really excited by is we have this idea of having noisy circuits, which you guys, I see it as continuum, noisy circuits which you're using today. Error mitigation was a concept we developed where we essentially make a observable have a better value by repeating many, many circuits and adding them together in algorithmic ways to suppress the noise. I like to think of it as a magnifying glass or something like that. And then fault tolerance, we all know Shor's algorithm and how it works, and by encoding, we can make error correction and exponentially suppress the errors with polynomial overhead, and that's where we want to get. So can we make it a continuum? In this work, we started with hypothetical. We said, well, in error correction, the T gates is the most expensive, and it actually uses a lot of resources to make these magic states. And in the other gates that are closer to the code can be done transversely. And so we imagine, well, can we error correct them? And then can we error mitigate the T gates? And we came up with techniques that showed that this is possible. We randomized over different types of polys, depolarized the noise, came up with a way that we could measure the noise coefficient, feed that into an error mitigation routine, and then calculate the effective of the observable of this type of circuit. And what the results found was that there might be this interesting domain that exists where, depending on the error of the T gate that you do, I can do more T gates than are feasible to simulate. The best known simulation methods, when we take T gates into account, can do about 50 T gates. And so this gives us an interesting area where we could have something provable and that we couldn't simulate. Or provable is a strong word. Something that we believe is very hard to simulate. So I see this being a continuum, and I see many, many techniques being developed that bring new and new ideas from error mitigation. I agree that we'll need error correction, but I see this as a continuum, and I think we'll build devices that will be capable, more and more capable to exploit error rates that are very low, that we can do more and more novel techniques. And I think this is going to be, in the next few years, we're going to see a lot more new ideas of how we mitigate errors, how we correct errors in different ways that are very application dependent.
Oh, okay. So one last question. So at present, is it feasible to use parallel computing with QPUs?
Is it, sorry?
At present, is it feasible to use parallel computing with QPUs? By this, I think the author meant that is it possible to use quantum computers in parallel and for dividing tasks? Is it possible or feasible right now?
So if you take in the water example, we ran it on a larger system and we broke it up into individual ones that we ran in parallel. So you can do things like that, but you're going to require that there's no quantum communication between the parallel. If I require quantum communication between the parallel channels, then we generally, at the moment, the best idea is to go to a larger system. But I think it's a great question of, as we go towards more distributed systems, how do we make compilers and algorithms that can have some load run on a set of gates that have very fast interactions and a set of gates that have very slow interactions? And how do we best take this into account? I would say we don't have many good results there yet, and that's going to become more and more important. And so the general idea of how do we distribute a quantum computation over a distributed modular future system, I think, is unanswered.
Okay. So thank you, Jack. Thank you, Jay. Thank you very much. This whole thing was very inspiring. And we hope that students from here learn and do much better things related to this. And thank you. Get well soon. Thank you all the participants who participated and people from IBM who helped us and QAQT in this talk. So for more, if you want to know more about Qiskit events, please sign up and follow the link. Thank you very much.
Thank you, Jay.
Okay. Thank you.
Very enjoyable talk. Really enjoyed it. Thank you.
Yeah. Bye.
Very polite guy. You can see from his face. Very polite.
He was sick. वो बीमार लग रहा था.
हाँ लग रहा है. उनका weather आजकल भी थोड़ा ठीक नहीं है उधर. US में बारिश हो रहा है. आ रहा है कुछ साइक्लोन.
Professor Panigrahi? Hello?
Solomon.
Yes, sir. How are you?
Yeah, you can actually open your microphone and also video. Solomon, I'm not able to see you.
Yes, sir.
Yeah. You are able to see me now?
Yes, sir.
How are you?
Fine, sir.
I remember last time 2019, you guys are here.
Yes, sir. Yes.
What kind of change takes place? So fast. So you are now obviously in the campus, huh?
Yes. I'm now in the office. I'll go home after the talk. So
yeah, okay. So RPG will be chairing your session, Professor RP Singh.
What chair? I'm just moderating, not chairing. No chair here. Just moderation. What moderation? Hi Solomon, how are you?
Fine, sir.
Fine. How is IST? Anything new?
Nothing new, sir. Here we're only class. Online.
Okay. Ashok is happy, but there. He says he has good company. Solomon is there.
Yeah, but now nothing. Lab we are not able to go now, sir. Like everything is locked, and students we cannot
Not able to discuss. That's the problem.
No, access also, lab access is now all cut. We cannot go.
Okay.
So those who are going into the lab means one student at a time, something like that. So rules are there.
Yeah, we are relaxed a little bit. We are allowing 4 people for 750 square meter.
I don't have any rule. Anybody can come. Yeah. So everybody is coming here. Yeah.
PRN is a small place. यार हमारा इधर क्या होता है?
Yeah, it is a small place. That's why.
बच्चे लोग
It's a small place. Yeah, not. You are right. Okay, it's time. We can start now, I think, na?
You can start.
Okay. So it's a pleasure to introduce Solomon, today's speaker, evening speaker. And all of you are welcome to QIQT. And I think most of you must be regular, listening talks every day in QIQT. And must be enjoying. Please ask questions. Okay, so as many as you like. Rather, even if you don't like asking, force yourself to ask questions. That way, speaker will feel happy that people are responding to his her talk. Okay. In online talks, really, if you don't ask question, it's really it's very bad. Like you just talk for 1 hour and then 1 or 2 questions comes, you feel like it is useless to give a talk. Anyway, so Solomon did his PhD from Math Science with Professor Simon, and after doing his PhD in Quantum Information, Quantum Optics, he joined IST Trivandrum, and there he has developed an independent group, but doing very well in quantum information theory. He has worked in classical optics, quantum optics, all sorts of fields. He is working on like OM states also. Work very closely to experimentalists. It's not like abstract theory, just mathematics. So he is working closely to experimentalists. Suggested many something very like some novel suggestions which can be done experimentally. One can do in quantum optics as well as classical optics in the lab. So with these words, I invite Solomon to give his talk. Okay, and please ask questions, as many as you feel like. Asking questions is very important in all more in the online sessions. Okay, fine. Solomon.
Yes, sir. So first of all, I would like to thank Professor Panigrahi and the organizers for inviting me, and also thank Professor R.P. Singh for this very kind introduction. So only we know what we are worth. Okay. So Professor R.P. Singh tells big statements, very good statements. So I am not, maybe I can say not as close as to what he portrayed. We'll do something. Okay. So today, what I'll be talking on is some very elementary experiment which gives us a way to demonstrate entanglement purely using classical optics. Whatever equipment you find in the lab, for example, beam splitter, mirror, laser, helium neon laser, all not very costly equipment, very standard BSc, BTech or MSc lab kind of equipment. So I'll be talking about this work. It's somewhat old, which is more than a year old now. But I thought since the audience is very young and all are students, I believe you will appreciate that very simple idea of demonstrating entanglement in a BTech lab. So let me share screen, which is for the PDF. Let me see. So people are able to see the slide?
Yeah, it's coming. Yeah, it is there.
Okay. So this is the title of the talk, Demonstrating Classical Optic Entanglement in an Interferometer. Okay, so stop and ask when you feel doubts. Maybe I will be able to answer most of the questions. If not, we can discuss. Okay, so let me continue. Okay, so what is the idea here? We are working, the idea is to work with what we call as spatial polarization entanglement. So everybody understands Maxwell's equations, right? Most of you have come across Maxwell's equations, which you solve in your graduate courses. Yes or no?
Yes, we should presume that.
No response from the students.
Yeah, that is the online thing. Yeah, it's difficult.
Okay, so I assume that you know this thing. So this is as elementary as I say. If anybody has solved Griffith book, you solve Maxwell's equation. At least the planar solutions you solve. There you will, you would have learned in high school. The polarization has, is a transverse field. You would have got 2 marks for that. It is, it propagates along Z, then X and Y are there. It is a transverse propagating wave. So that is essentially the idea here. But then the question that is asked here is, what can we say about, in particular, can we manipulate or, understand that polarization concept better? Okay, so that is, and is entanglement there in that very elementary context? Okay, so that will be the first thing which I will discuss. The second thing is, if such a thing is there, can we demonstrate or detect entanglement through fringe movement? So fringes, everybody, you would have seen in your high school, undergrad school or high school, maybe, I don't know, Newton's rings, whichever experiment you did, you would have seen fringes. When light waves interfere, you see fringes. Question is, can we, through the fringes, can we detect entanglement? Then the third will be estimating such a entanglement, can we estimate it through intensity measurements? Okay, so then I will go to the experimental setup, which is very elementary, and then maybe outline some results and then summary of what has been achieved. Okay, so this is the outline of the talk. So now let me go to the next slide, which is, okay, so now a brief discussion on what we mean by a paraxial coherent vector light field. Okay, so let me come back to the Griffith picture. So we had a wave propagating along z-axis maybe. Then it had components, electric field components along the x and y axis. And then the description of quote-unquote polarization per se is simply to characterize what all you can do with those x and y components, how we can describe those x and y components. Now, if you see carefully through Griffith, for example, what was missing there or what is not stated explicitly is that, okay, we have plane wave solutions, but in general, or there are more general situations. So what could happen? So the thing is, if you have transverse components, we never saw in Griffith that the transverse components could be dependent, the amplitude of the transverse components could be point-wise specific. Okay. Now that was missing in our elementary treatment of polarization. But real life, okay, we don't deal with plane waves, we deal with laser light field, which is not plane wave, it is some Gaussian shape. And so it is suspecting now that we can have actually polarization which is point-wise spatially dependent in the transverse plane. Okay, is this clear to everybody?
I think you have to explain a bit more, Solomon, this point. Yeah.
So let me rephrase and reword whatever I said. So we had plane wave solutions of Maxwell. So there, if you recollect, you would have simply solved, you would have put a e power I kz minus omega t. The amplitude was simply E naught. Correct? You never told E naught is a function of x and y, that it can be a function of the transverse coordinate. Okay, but in reality, in practice, we work with not with plane waves, but with things like laser field. Such a thing, by now, whoever has used laser pointer knows that it has a spatial distribution, meaning the intensity is not the same across the transverse, at all points in the transverse plane. There's a modulation, a Gaussian modulation. In particular, we can have the polarization itself to be modulated as a function of x and y. So that is the expression that I have written here. In this psi tilde of xy is a1 psi 1 of x comma y. 0 simply denotes the fact that it is say maybe horizontal polarization, and then there is a a2 psi 2 of x comma y with vertical polarization. Okay, so for every point x comma y, you will have a polarization state. That is the idea in this expression. Okay, now you can write that in a column vector form in this form, as a column 2 cross 1 matrix column vector. And now, you can also, as you would have, polarization can be any complex linear superposition. So you could actually put in coefficients A1 and A2 in front of each of the components. Okay? So far, so good. I think somebody can say an yes or a no, please.
Yes, sir.
Huh?
Yes, yeah, it's okay. It's okay. Go
Okay,
ahead.
okay.
Yeah. I think
Okay.
it's clear now. Clear, yeah.
Yeah, so now let us look at, hopefully by now you would have got a dose of entanglement from most of the other talks, correct?
Yeah, they have been listening for so many days. Yeah, since.
Yes, okay. So now at least we know what is, so now here we have 2 degrees of freedom. One is the polarization degree of freedom. Other is a spatial degree of freedom. Okay. So now what I have written here is a simple example of something which is a product in polarization and space. Okay. Now, so this is a very simple form of a simple example of a paraxial light field, which is, the whole thing is separated out. Polarization is separate, spatial modulation is separate, which means at any xy, if you measure the polarization, you will get A1, A2. It doesn't matter. The overall factor may be different, depending on what psi naught actually is. But up to that overall factor, the polarization itself is simply A1, A2. Okay. Now, any paraxial vector field which cannot be written in this form, then by now you know the definition of entanglement. Probably you would have heard of Schmidt decomposition, canonical form, all those things you would have heard by now. So it's understandable that if something is not, the polarization state or the paraxial light field cannot be written in this form, then we can say it is polarization spatial entangled. Okay? Is this clear? Okay, so now let me go to the next slide. Okay, so now, so everybody understands hopefully what is a linear polarizer, I presume. Okay, linear polarizer is basically in the quantum mechanical sense is it projects into a particular state of polarization. Okay, so now you look at take a product polarization spatial vector field. You project it with this linear polarizer. This, a cos theta, this matrix, which is a linear polarizer oriented at angle theta in the xy plane. Okay. Then a simple calculation, you just project it calculate the intensity. Intensity is nothing but after you have projected it into the particular polarization state, calculate the sum of the x and y component squares. So if you did that calculation, you get this expression, simple expression. It simply says that your state of polarization, which was A1, A2, now gets projected into that this particular linear polarization, and the intensity is simply, because you projected it, there is a modulation of the intensity by this much amount into an overall modulation of spatial modulation, which was already present through psi naught of x comma y. Okay, this is very important for the what follows. So let me pause for a moment. If there are questions, kindly ask me at this stage.
You can ask questions if you have questions.
At this stage, yeah, if there's something, you have doubts, please ask.
Unmute yourself and ask questions if you want to ask. I think Solomon, nobody is asking question. Anyway, Solomon, one thing is there. You have a special degree of freedom, you are saying. So
yes,
there is x and y. So can you take it 2 degree of freedom or only 1 degree of freedom? Like you have x also, y also.
X and y both are there, sir.
Both are there. So you will take it as 1 degree of freedom, special degree, or there are 2 degrees of freedom. Like
okay. So I will treat the whole xy as 1 complete degree of freedom. Of course, there are x and y variables.
Can you consider it as 2 degrees of freedom also?
Yes. But then that degree of freedom is a separate story. I don't want to distinguish that xy divide. I want to put them, it is like some tripartite kind of thing.
So it is tripartite. That's what I think. Can one talk of this kind of things in this kind of
Yes. People have talked, I think, yes. Okay. But here I am only talking about
right now you are talking that. That's I was thinking somebody can,
So this is only bipartite. I have divided the space part as separate completely. XY, whatever it is, I have clubbed into one function. Polarization A1, A2, I have clubbed into the other portion.
Yeah.
Okay. So if you look at this expression I of x comma y, you see there is this projected amount thing, and then there is a spatial thing. They come as a product. Now what does that mean? It simply means that if I vary theta, I can vary theta of the polarizer. If I vary theta, I rotated the polarizer, then this intensity is always there in the background. This is simply a overall factor, which is simply function of simply theta. It's a function of theta into function of x comma y. So whatever this function of x comma y, the psi naught of x comma y mod square is there, it will simply modulate by this amount. Okay, this can go to 0. That is not ruled out. This mod square can go to 0, but it will simply either this will be fully visible or not visible. It will be the same thing, going bright and dark. That's all. There's no change in shape of the intensity. This is the intensity. This is simply the modulated intensity by function of theta. Okay, which means there is no fringe movement, or there is no movement at all whatsoever of the intensity. The intensity is as it is, stationary in the xy plane. It simply brightens and dims. That's all what happens when you rotate the polarizer. Okay, so now let us go to the next situation. Now you look at a fellow who is which is not separable, which is not a product in the spatial and polarization degrees of freedom. Now if you project it, okay, a simple algebra, you project this fellow, do the thing again, do the same thing, intensity, just take the mod square of this column vector, the resultant column vector, you will get this expression. Now if you look at this expression, it looks like the interference of psi 1 of xy times c theta a1 with psi 2 of x comma y a2 s theta. These two amplitudes are interfering, and we are plotting that the intensity, the resultant intensity, basically. Okay. So now you see, now this the theta and space part is not separate now. Theta is sitting inside as comes as a coefficient of the two wave functions, psi1 of x comma y and psi2 of x comma y. So,
Luman, have you shown that this field, this A1 psi1 xy, this matrix, this field, vector light field, it is non-separable? Have you shown earlier? Students may not follow, like why it is this non-separable, this
no, okay, so that means then I have to go to, oh my god, I don't have a board.
No, not a problem, because you have not shown in earlier slide that this is non-separable.
Okay, so let us go to the, so I need some response, at least from one or two of you. So everybody knows the Schmidt decomposition?
I doubt they will respond, but anyway, I am responding, don't worry. So
no, sir, not you. I need, because I even till last week I was teaching classes. So if somebody says yes or no, then I can immediately tell. If I don't know what is in their mind. So everybody knows Schmidt decomposition, at least few of you.
Students, please students, if students are around, please say something. Yeah, please respond to his.
Or people have gone for dinner. They have simply muted and gone for dinner.
This is hazard of online. You never know, who are there,
So see, in Schmidt decomposition, right? Meaning, if you write any vector in, say, bipartite system, you take the most general linear combination, correct? There is no reason to expect that any state in a bipartite system is separable. See, separable is very special. Let me go to the separable definition. Let me go to the previous two slides. This, only if it is of this form, it is a product. Okay. So in general, you don't expect something to be a product. That means something like A1 psi1, A2 psi2 need not be written as some A1, A2 into some psi of x comma y. This psi1 and psi2 can be different. If they are different, then there is, you cannot split it. You cannot factorize the thing into polarization and spatial part. Which means intuitively, that means we have entanglement.
Yeah, that's fine now.
Okay. So now, because of that, if you project it to the polarizer, the intensity now comes out not like the previous form. Now it is superposition of two waves. One with psi1, psi1 of x comma y, another is psi2 of x comma y. The amplitudes are modulated by c theta and s theta, sin theta and cos theta. Now, which means if you vary theta, because now if you vary theta, you are going to change the amount of psi2 and amount of psi1 relatively. So the interference pattern can change, which means the movement of intensity will move. Consequently, if the intensities can move, then the zeros of the intensity also can move. So what is fringe movement? Fringe movement simply means that, if you take an interferometer, you recombine, maybe something like a Michelson, you recombine, maybe you see straight line fringes, and maybe you move one of the arms, one mirror, you move a little bit, the fringe will move. Basically, the zeros of the intensity are moving. That is how we see fringe movement. Okay. Now, it's understandable that now same thing can happen here. Now, because it's two different waves, I am modulating the relative amplitudes with cos theta and sin theta. So, depending on what cos theta and sin theta are, the intensity can get modulated accordingly, which means the zeros can move, and consequently, that is, we can reinterpret that as, when the polarizer is rotated, fringes can move, indicating the presence of spatial polarization entanglement. Okay. Okay. So let me go to the next slide. Okay. However, now can we ask a converse question? Are there examples of light fields which are entangled but show no fringe movement. Okay, so the answer is yes. Those of you who have gone into optics maybe can recognize this. So something which is called as the Logger Gaussian mode. So I don't want to go into much details of this. This is what is called as in classical optics and in quantum optics also people call this as the LG mode. There are solutions of the Maxwell's paraxial wave equation. So this +1 means something, whatever it means. Basically this LG +1 and LG -1 are orthogonal and they are already in Schmidt form. You understand? So this has polarization horizontal with LG plus vertical with LG minus. So it's already in Schmidt form and it is maximally spatially polarization entangled. Okay. Now this LG has a particular special form. It is circularly symmetric. So both are same intensity pattern actually. So you cannot distinguish the LG +1 and LG -1 purely from its intensity. So if you actually calculate now, you pass it through a rotated polarizer. Do the same calculation. This because it is rotationally circularly symmetric. The psi of r comes out, and in this case again the intensity is independent of theta, even though the state of polarization is maximally entangled in the polarization spatial degree of freedom. Okay, so fringe movement cannot always see. First of all, we need coherent light field, which means there is it's well defined polarization. On the top of it, fringe movement may or may not detect polarization spatial entanglement. So this counterexample gives this is a simple counterexample. Maybe there are many more examples which bypass the system basically. This is clear. So we can conclude that what do we conclude? Fringe movement under rotation of a polarizer is a sufficient but not necessary condition for detecting spatial polarization entanglement in coherent light fields. Okay, so this is one of the key this is the main content of the work basically. So at this stage, any questions are there? Please ask. Again, I'm asking you to ask questions. Otherwise, it becomes like a monologue.
Yeah.
Maybe RP Singh sir should not ask. I think somebody else should ask.
I will not ask. Somebody from his students should ask. Yeah. There are so many questions in chat. I don't know. It's not. There is one question in chat. Is it possible to create an entanglement while there is lightning in the sky?
Maybe, I don't know. We'll have to see. See, lightning is, at least I don't understand lightning. I don't know. Maybe people, experts in that field understand it. But of course, the entanglement is a property, any Maxwell, anything obeying Maxwell's law, equations. Any electromagnetic field should obey it.
Hello. Somebody was trying to ask something, some mic problem, or whether one can. Hello. I don't see. So you were answering the question for lightning, Solomon. You can.
Yeah. So any electromagnetic wave can have so-called quote-unquote spatial polarization entanglement. If it is if you can form solutions or whatever, you just propagate it. Propagation can in fact maybe generate entanglement for you. All we have to solve the equations, but it's not ruled out. There's no reason why it should not be there. Okay. Okay. So let us now move to the Now this is a. Maybe should I go to the actual? Yeah, this is the setup. So let me go to the setup straight away. So So this is a schematic. So there is an input. You have a lens to, maybe, enlarge whatever, control the divergence of the laser light field. Something like a laser pointer basically coming in. There is a polarizer P1, which controls the input state of polarization. So this device is what we call as a polarizing beam splitter. So this is a very nice device. It is little more sophisticated than a regular beam splitter in that thing that depending on the state of polarization, whatever be the state of incoming polarization, it will always allow, in one arm, for example, horizontal, in the other arm, vertical. Okay. So that is a specialty of this device, what we call as the polarizing beam splitter. Okay. So, suppose you put a 45-degree polarization, you put this P1 at 45 degree, then this fellow will split. For example, the horizontal component of that 45 will go through this way, the vertical will go through this way, and these mirrors are in this particular angle so that you can close the loop, and then they will recombine again here. Again it will transmit back. The vertical will come back here, the horizontal will also come back. Whichever way they take, they'll come back and recombine and join here. All the while maintaining quote-unquote coherence. By coherence, we mean the superposition, whatever was sent is not destroyed by one fellow going clockwise and other fellow going anti-clockwise. Is this clear?
Yes, sir.
Okay. So you understand setup. So there's just a lens to control the divergence of the laser field. P1 is just a polarizer to control the input polarization. So when you put a polarizer here, what will happen is the state of polarization is of this form. Of which form? Let me tell you. Of the product form. Because you have collapsed, some spatial thing is there and you have fixed the polarization universally across all points in space to some A1, A2. That is what a polarizer does actually. Okay. It will fix the spatial thing once for all. Then this whatever be the space thing, and then this polarization is fixed for all points in space, all points in XY. Okay, the same polarization is there. That's what polarizer does. So that's what this fellow will do. Let me come back to the diagram. So this polarizer basically makes it into a product state. Now the question is whether this kind of an interferometer can generate entanglement. So that is what we tried to see. So what did we do? So you put up PBS, polarizing beam splitter. It will split, horizontal maybe this way and vertical this way. One goes clockwise, other goes anti-clockwise. Then you recombine here. Now, so let me tell the practical aspect of it. There is no, ideal. There's no practical way to actually make these mirrors all exactly the same angle, perfectly aligned, such that there is zero misalignment in the recombined beams. Is this clear to people? Those of you who have done experiments in the lab, hopefully you know that there is no way you can, for example, in Michelson or in this setup, there is no way you can arrange the PBS exactly perpendicular. This line is exactly, this horizontal line is perpendicular to this vertical. There is no way you can do that. Maybe you will get 89 point some degree, maybe 89.8 or 18.89, whatever. There's nothing called, you cannot make something like 90 exact. Similarly, this cannot be made 45 exact. You understand? There is no way you can, this diagram is slightly misleading, I think. There's no way you can fix the angles exactly symmetrically the way you want it. Okay. So now that means, mirrors M1 and M2 can introduce quote-unquote tilt. Tilt means basically that is what will, relative shifts, which gives rise to, the relative shifts are there. And then on recombination, you will not know what went in as a product. What comes out on recombination are like, there are displacements. One polarization gets displaced by one amount in the XY plane. The other fellow gets displaced by a different amount in the XY plane. Okay. So there is no reason on recombination at one clockwise, anti-clockwise, and recombine, that they come back to the original product form. So what is entering here is polarized. It's in product form in the spatial polarization spatial degrees of freedom. This mirrors can give lateral displacements to the light field for the horizontal and vertical components in a very different manner. Horizontal can pick up a lateral shift, in one way, and vertical can pick it in slightly different way. On recombining, there is no reason to expect that whatever is recombined is of product form in polarization spatial degrees of freedom. Okay. So now, you forget about this P2 and this, polarizer 2 at 45, quarter wave plate at 0. This is to do estimation of entanglement. Okay. So what we do is actually, you forget this dotted thing. So what you do, you recombine field to test for entanglement. The simplest thing you do, you insert a polarizer, rotate it. Okay. As we discussed earlier, you take a field, whatever field, if it is entangled, it should show on rotation of a polarizer, it should show fringe movement. For which is something that is separable, it will not show fringe movement. So that is the idea. You don't even need a CCD camera, mind you. You can put a simple pad, notepad or a note. You just put it, hold the notebook vertically, across, and make your notebook as a screen. You will see fringes. Okay, it's as simple as that. Most of you, I think, would have done, at least those of in MSc or BSc would have done some optics interferometry experiment in such a manner, I'm sure. Okay, this CCD camera is for estimating entanglement, that I don't want to go into. So this is just to, you can put as a simple white paper stuck onto a pad, and you can hold the pad perpendicular to the the direction of propagation of the light field. Okay, it's as simple as that. So now let me instead of going into the calculations, you see this. This is what actually we this is some recorded fringes actually. You see the top one and you see the bottom one. Can you see some difference between the top and bottom? And if so, it's like I'm asking you to solve like in our cartoon books, you have, simple books, comic books. They will tell you spot the difference between the two pictures. So I want you to spot and tell me what is the difference between the top row of fringes and the bottom row of fringes. Somebody, please. Nobody wants to speak.
Sir, the fringes have, that below one is sharper compared to the top one.
The lower one.
See, that is one observation, yeah. See, fringes below are sharper, yeah. That's what they're saying.
Sharper?
Yeah.
Yeah, and one more thing. Can you see that they're the same actually? Simply the modulation is their overall modulation. They're exactly the same. Except that, there is simply the dimming of the intensity. That's all there is. There's the same three fringes, basically.
Three fringes, yeah, at same places, yeah. Just
same place. There is no nothing. Basically, this is the separable kind of thing. You take a polarizer, first you polarize the beam. So, for a polarized light field, it is already separable. Then you take another polarizer and simply rotate it. This is what you will find actually. You will get, suppose you are able to form fringes. The fringes will be as they are, no movement whatsoever, quote unquote. The zeros also means this, you can see the dark fringe, right? So they will remain wherever they are. They're stationary, no movement. But on the contrary, you see the top fellow, see the A2 and A3, there is some smudging kind of thing, something rearrangement of intensity is happening. So you look at the first fellow, this is where the interference, you can see the zeros. When you moved, when you rotated the polarizer, you found that, some blurring happened, some rearrangement of intensities took place. Then, if you actually look closely further, A4, A5, if you superpose A4 or A5 with A1, you will actually see that, what is the dark of A5 is where the location of the dark of the A5 is there A1's bright is there actually. Okay, so that is what is highlighted in this E1. So this dotted is what happens under movement. You can see the, one is the background, which is like say A1 perhaps. The other one, the dotted are the ones which show the moved fellows. Is this clear?
Yes, sir.
Okay. So this is the thing which I wanted to convey to you people, that you can actually set up a very simple interferometry experiment and demonstrate. So this all this that this says is that lower set of fringes demonstrate quote unquote you are it is okay it's concurrent with the fact that there is no entanglement quote unquote. The top fellow fringes are moved. You can conclude that of course obviously there should be polarization spatial entanglement. Okay, it's as simple as this. So this is this can be demonstrated very straightforward. Put a setup. Take a chart paper or whatever. Your notebook, white sheet. Flash it across the laser field. Once you have aligned it, quote unquote. That is a little tricky. Okay, some experience is required. Those who have done in 2 hours or 1 hour, you should be able to do it. It's not very difficult. Then you simply rotate a polarizer. This polarizer you rotate. This setup. This polarizer P3 you rotate. And that's it. If the fringes move or there's a blur, the movement of intensity is there, you conclude that there is polarization spatial entanglement. Okay. So the other thing is about I don't want to go into these details of this calculation, how much entanglement was there and so on and so forth. These are all little technical, maybe beyond the scope of some of the students at least. So anyhow, that's this has to do something with concurrence. And by the way, one thing I would like to remark, the entanglement is exactly calculated the same way you would do in a split decomposition. For example, let me tell you this. I hope people understand this part. Okay, this I write a density matrix. So if you have to calculate entanglement for a bipartite state, what would I do? Have people calculated by partial trace? Some of you at least say yes or no.
They say yes, sir. Yeah, at least one person says yes, sir.
Okay, very good. So all I'm doing here is, when I'm saying estimating spatial, entanglement, whatever, through intensity measurements, basically I'm calculating partial trace. Basically, you can see, I'm integrating out the, intensities, the spatial degree of freedom. I will get a qubit, basically. This rho p is a qubit. So if I calculate the entropy of this qubit, I have a measure of entanglement. So how to calculate, trace away the spatial degrees of freedom is, those who have done, polarimetry, quote unquote, Stokes parameter measurement experiment will realize that, this is nothing different. The same thing, hopefully some of you at least have done, Stokes parameter measurement in your lab, using quarter wave plate or, using wave plates and polarizers and so on. That is exactly the calculation, and this is nothing more than partial trace. And the entropy of this rho p, trace rho p, ln rho p, whatever, that S of rho p, that gives you simply, concurrence, whatever, all those things are calculated simply using rho p. Okay. So I think I will stop here. I don't want its time. So I think 45 minutes I've consumed. So if there are any questions, kindly now ask.
Solomon, you have written very nice paper, this work which you are presenting, very nicely written paper. Can you just tell them reference of the paper at least?
Reference, this is a paper.
Yeah.
This is a paper.
If they read, yeah.
Yeah, this is a
All
paper.
of you please note down this reference, and you can read this paper, very nicely written paper. You can follow that, and you are free to ask questions. Yeah, please. Go ahead and ask questions, whoever is there.
RPG, can I go?
Yeah, sure.
Yeah, hi Solomon, Shivakumar here.
Yes.
So my question is something to do with what originally RP Singh asked. So you have two spatial degrees of freedom which you have practically clubbed as one and the other one. But is it really quantum entanglement?
No. This is very classical. We are only demonstrating entanglement phenomena. It is not quantum. It is simple optical. Entanglement is a notion coming from superposition principle.
Yeah.
Okay. So it is not quantum. Quantum means you need measurement, collapse phosphate, all those you need. Like photon, single
that's what I
photon,
was
that kind of
wondering.
thing.
Because, in fact, I was about to ask you the next question, like, can we really demonstrate anything like that in a simple setup? For instance, establishing the bell type correlation and things like that. So obviously it won't happen here.
The correlations you can do, because I think the same student is now working on some other actually, okay. Professor R.P. Singh also will know that meaning correlates you can actually establish.
Shiva, you can derive this Bell inequality and all those things, even this kind of setups. Okay.
Mm-hmm.
So not a problem, but this is basically based on correlation. You can find those correlation coefficients and you can derive Bell inequality. You will
so Professor
getting violated.
See, R.P. Singh ji has done very good experiment. I think you should look into that experiment and Bell inequality violation in same kind of right fields.
Yeah. So you can see that paper, very well written. Chitra Bhanu, if you see, yes, paper on this Bell inequality violation in this classical system. So.
Okay, thank you.
Any other question? Subimal, are you there? Subimal, Minal? Okay, Minal has question. Let us see. Sir, how do we differentiate between classical and quantum entanglement?
Oh, okay, very tricky question, but okay. At least the way I understand is in quantum, this there is this collapse postulate. See, of course, this classical light is also made of continuous streams of photons, each coming one by one, but very fast. Maybe the time interval is you don't have enough. There are too much of them that you don't differentiate which photon is which. But for I believe at least the way I understand is for something to be quantum, you need that if suppose the same PBS, you take a single photon incident on this PBS. Suppose. See now let me go to the diagram. Yeah. So this PBS, instead of saying I have 45-degree polarization of a continuous laser field coming in, suppose I am able to send I attenuate it, send it single photon by photon. This PBS, if I understand correctly, what it will do is the photon now it can either go this side or this side, which means quote unquote it will it will collapse into either the right path or the left path. And I think that is when you call things quantum. Then there is actually, you have done sort of a measurement, quote unquote. Okay, that is not available, even in the continuous case, too many photons are there, they're streaming in. The degrees of freedom are entangled, quote unquote, but we cannot say that we have collapsed because there's too much of them. And we cannot infer something as being collapsed or not collapsed from this kind of thing.
So it's degrees of freedom which are entangled here. So Solomon, there is another question. There is some medical surgeon, okay, Aniket. So his question is, after coming to quantum, sir, being a surgeon, my question is a bit out of the box. Okay. You see the further development after coming quantum methodology in the field of precision medical surgery, or rather any further development laser after coming of quantum technique.
Yeah, quantum, I don't know. My colleague, Professor R.P. Singh student.
Level.
So Ashok ji is the expert on that. Okay, see what I realized from talking to Ashok and hearing him in talks and all that. See, there is I think lot of work going on in this sensitivity of an optical device basically. First of all CCD camera, then light itself. Can you make it? How can you manipulate the property of light itself to enhance your sensitivity? Of course, as I understand literature, yes, a lot of sensors are being built. People have made it using actually quote unquote quantum sources which show quote unquote significant improvement over the kind of laser which was used in this setup. For example, this is a simple continuous wave 633 nanometer. laser pointer kind of, that kind of laser source. What is used in those kind of experiments, you need specialized, you need to process. The field is not readily made. You need nonlinear devices, nonlinear materials, and then manipulate the properties of photons at the, it's little involved. It's not easy, but it is done. The people have done a lot of experiments. So that will be my answer to your question or comment.
So Aniket, I have also comment here. There is application in biological imaging. You can have better imaging, and once the biology is basically microscope, you look at them through the microscope most of the diagnostics. So you can have you can improve on the imaging, and you can differentiate cells which are diseased or which are normal cells much more clearly. So that is one, and mainly in biological imaging, you can have better imaging, and then you can differentiate your. It will be helpful in diagnostics. So that way, it is going to help this quantum sources of light squeeze or entangled photons. They are helping in that. Okay, you can have better imaging and much more clear differentiation when you are going for diagnostics. That is one thing. There are other magnetic resonance imaging. It's being used now, or defect centers in diamonds. A very compact resonance imaging device is being made, and with very less magnetic field and very compact, you can do the MRI much more precise. So there are other applications also coming in. So quantum technology, quantum science is going to affect new devices are going to come in medical field also using quantum. Okay, Sen Solomon, there is one question.
Yes, sir.
Is there any other type of Abel George? He's asking Abel George Koshi. Is there any other type of polarization entanglement other than spatial polarization? So
yeah, no, I don't know. Eberle wrote a paper. He wrote, hidden coherences or something. I'm not exactly recollecting the paper. 2015 or 16.
Mm-hmm.
So I don't know. Space. It is. I think you'll have to read his paper. Even I didn't understand. Then he wrote that something called hidden coherences in light fields or something like that. That was the title of the paper, if I recollect correctly. You'll have to read his paper, 2015 or 16. I'm not sure. Eberle and his students, some of them, they wrote, perhaps, I'm not sure which journal. Because this coherence, what I understand is, light and matter are dual. Okay, so of course there is spatial polarization, but okay, you'll have to carefully look into what are the degrees of freedom available in light. So it's not space, then there is, things like angular momentum, these kind of things are all there now.
Yeah, orbital momentum, yeah. And another degree of freedom can be orbital momentum and polarization. So that is also, you can show the entanglement there also, other than spatial. You can have polarization and orbital momentum of light. These 2 degrees of freedom also one can show entanglement. So similar, you can look for other degrees of freedom. This certainly orbital momentum and polarization one can easily. So that is the answer. And then one more question is there, Solomon.
Yes, sir.
Can we create such classical correlations for fermions like electrons?
Fermion entanglement is a very non-trivial object. Let me recollect from my whatever I learned in math science from one's very senior professor. At least then it was a unsolved problem. I don't know, Professor Panigiri might know better on this, because fermion by definition is an antisymmetric wave function. Okay. By definition, you have to put it as a singlet kind of a thing, 0, 1, minus 1, 0 kind of a thing, because if you flip, it should get a minus sign. Now, so the question was whether, fermions are entangled by definition, or how do we define entanglement for fermions? So there is one paper by Professor A.P. Balachandran in 2010. whoever has asked that question, please, I didn't understand that paper. That paper, at least it's a PRL paper. It is supposed to have solved that fermionic entanglement, because definition of entanglement itself is, at least to my knowledge, was controversial in fermion context. At least from my hearsay, the talk or whatever discussions that were there in Mad Science during my stay there, that was 10 years ago. I recollect that Professor A.P. Balachandran came up with some new definition or new way to look at entanglement in fermionic systems. So I'm not sure. Mimicking and all, I'm not sure. Because even definition is very tricky. Though people take, they define it as if it is regular, like bosonic entanglement, but bosons are, the entanglement, the structure is well defined. Hilbert space is well defined, or separability and all is a well defined notion. For fermion, the state itself, you need the antisymmetric wave functions, and that by definition is entangled, quote unquote. So I'm not sure how.
Yeah, people do talk of this electron entanglement. Naresh Chandra from IIT Kharagpur, very old papers are there. They talk of this entanglement of electrons and all. So they are papers, but as Solomon is saying, yeah, it's not very clear. Yeah, when it comes to fermionic system. So I don't see any other question. They are saying thank you, sir, for wonderful talk. Very nice talk, wonderful. That's what they're saying. Other than that, I don't see any question. But Subimal is there listening talks. He can ask questions. Subimal.
Yes, sir.
Are you there?
Yes, sir. Yes, sir.
Yeah.
But why don't you ask questions? Saurabh, you are there. You can ask questions. There are so many guys sitting there. They are not asking questions. At least ask some 1 or 2 questions. It's not so difficult talk that you can't ask. Yes, sir. They're saying they're not asking me still. I don't know. They are muted. Otherwise, we will conclude if nobody is asking question. Solomon.
Yes, sir.
Let me see. Still, we have few minutes.
Sir.
Yes.
We will wait for 2 minutes. Let's see.
Sir, I want to know which field right now you are working.
See, I am a survivor. Professor R.P. Singh ji says that I do many things, but see, researchers also like students. We are all students of physics. We struggle every day to look into new problems. So for now, I look both into quantum entanglement, whatever. And after coming to IIST, because of teaching undergrad optics lab, that is how I learned optics. And one Professor Murthy is here. Probably some of you are aware of him. He introduced me into the lab, to do undergrad experiments. That's how I learned optics. So I'm doing optics also now, classical optics, or this kind of, not more than this. Okay.
So one very nice thing Solomon has suggested, using these 2 thin lenses. Okay, simple convex lenses. You can implement all sorts of optical components. Okay, very nicely written paper. Okay, so classical optics. So he works in classical as well as quantum optics. He has very good understanding. So you can go to his website and see the papers. Or Google Scholar. You can see his papers. You will have very good idea what the fields he is working. Okay.
Yeah, sir. Really, sir. It is helpful, sir. Useful.
Yeah. And you can look through this paper also, which he has discussed. Very nicely written paper. You will be able to follow if you read carefully. Yeah. Any other question?
So what are the use of these separate components in front of P2 that you have skipped actually while explaining it?
Repeat.
So what are the separate components in front of P2? Like QW.
That is for estimating the thing, boss. You would have, I think, hopefully by now you would have, somebody would have taught you, or you would have come across this estimating a density matrix problem. Something like that.
Yes, sir. Yes.
How many measurements do you need to estimate a density matrix? This question somebody asked you. You remember? This question, like, you can measure only the diagonal entries. You remember that kind of a thing?
Yes, sir. Yes, sir.
Meaning, what you will do is, if you recollect for a qubit, you will keep on rotating the qubit appropriately. Unitaries, you will keep, because diagonal entries are the kind of things you can measure in an experiment. Because observables, some observable basically, it will collapse that thing into the eigenbasis, correct? Yes or no?
Right, sir. Right, sir.
You will get the observables, you will get the average value in that basis, correct? In some particular diagonal basis. Then you change the diagonal basis, you will get the, the average value in the rotated diagonal basis. You understand? So you can ask a question, how many such things you require minimal? Okay, meaning, how many such measurements, different measurements, which are mutually not compatible, or what we call, they're not the same diagonal basis. They're, rotated by some amounts. So only if you rotate can you measure the off diagonal entries of a density matrix. For example, you look at this, see, basically our goal is to measure this rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1 density matrix. So if I take simply trace, I will get rho 0, 0 plus rho 1, 1, which is already 1, normalized, suppose. Then how will I measure rho 0, 0? I have to project, this is nothing but the, projection into the X polarization or horizontal polarization. So what I will do, I will project it into horizontal, I'll put a horizontal polarizer and measure intensity. Then I will get rho 0, 0. Similarly, I'll put a vertical polarizer, measure intensity, I will get rho 1, 1. Then how do I get rho 0, 1, rho 1, 0? So for that, I will have to do a quarter wave plate is like some unitary transformation. You will bring the off diagonal entries into the diagonal. Okay. So that is what I use here. I will simply put, see for this example, this matrix 1, 0, 0, I. This is a quarter wave plate. Okay, that is that QWP. Then this I will move, it will apply the phase, it will move things, off diagonal entry into the diagonal part and so on. And then, that's what I'm using, quarter wave plate at 0 degree and so on. Is it clear?
Yes, sir. And so one more question is that here we are, instead of a usual beam splitter, we are using a polarized beam splitter.
Yeah.
So instead of using a single polarized beam splitter, can we use a separate, polarizer and then a beam split after it so as to make two components?
Yeah, I have not thought of it. Beam splitter will allow everything through, boss. This is like, what I'm doing here is I am shifting or, moving a laterally moving the polarizing individual polarizations separately, in two different ways. Because one is clockwise, other is anti-clockwise, and misalignments will be there. They will move. Right. But in regular BS, I'm not sure. I have to think, boss. You also think. Why don't you see if that can be done? Then that will be a work. Actually, PBS is costlier than BS. Actually, you'll have to see if actually.
Yes, sir,
BS,
because the overall fabrication cost
through.
will increase. In that way. Because if the beam splitter is itself polarized for this purpose, so overall fabrication cost will increase in that way.
Yeah. So BS will work, I think, because the tilts are different. This is what we call Sagnier configuration, as they call it. So one going anti-clockwise, I think it should work. Not sure. You have to check. I've not done the actual calculations. You have to actually see if the recombination, if you superpose the two polarizations back. A nice question, actually. You should think and try to see if it could be done. Okay. I will also try. I've not done the calculation.
Okay. So I think it's time. Prashant, you are there? Prashant ji, okay. Are you there?
Actually, he's a little bit busy.
No problem. It's okay. It's fine. So we can conclude, I think. Solomon, thank you very much for giving such a nice talk. And I think most of the students must have followed. Otherwise, they can go and read the paper. It's a very nicely written paper. Thank you, Solomon.
Yes, thank you, sir.
Okay, see you.
Yes, thank you. Good night. Yes.
We can leave, I think.
Yes.
You can stop sharing and...
Let me see. Something has happened. I'm not able to stop share. Stuck.
We are going to
stuck. Okay, no problem. Okay, fine. Yeah.
You can now it's it has come. Yeah.
Yeah, it's you have come out. Yeah, fine. Okay.
Yes, thank you, sir.
See you. Bye.